So let's take a little trip back to chapter 15 and let's define a electromagnetic wave. We're going to have the electric field and remember that's a vector, and we're just going to look at the y component, and that's equal to E naught times sine, remember the k of the wave, so it's kx minus omega t, and we're going to have for our magnetic field, that's going to be equal to the magnetic field in the z direction, and that's going to be B naught sine k of the wave minus omega t. Oh, and that should be an x, not an omega. Now remember from chapter 15 that k is also equal to 2 pi divided by the wavelength. Omega is equal to 2 pi times frequency, and that omega divided by k is equal to frequency times wavelength, and that's equal to the velocity of the wave. So let's start with our first relationship. We have the partial differential of the electric field with respect to x is equal to the negative partial differential of the magnetic field with respect to time. And if I put the electric field in for my partial differential of the electric field, and my magnetic field in for a partial differential, and I just have to differentiate with regards to the variables for each one. So for the electric field, it's going to be with respect to x. So using the chain rule, I'm going to have a k that comes out, and the sine goes to a cosine. And the omega t is just a constant because t is not the variable of differentiation. And on the other side, we're going to do the magnetic field, and since omega is negative, it's going to cancel out the negative for the differential, and I'm going to have omega times my magnetic field strength cosine kx minus omega t. The cosines are going to go away, and I'm going to get E naught over B naught is equal to omega over k, and that's equal to the velocity. Now we can do the same thing with the other relationship. Partial differential of the magnetic field with respect to x is equal to negative mu naught epsilon naught partial differential of the electric field with respect to time. Putting in my B field equation and my electric field equation, I get k B naught cosine kx minus omega t is equal to, well, omega is negative, so it's going to get rid of the negative sign in front here, and that leaves me with mu naught epsilon naught omega E naught cosine kx minus omega t. The cosine is going to go away, and I'm going to have B naught over E naught is equal to omega, or actually epsilon naught, mu naught, omega over k, and that's just equal to mu naught epsilon naught times the velocity. Now I can flip this, and I can have B naught over epsilon, or E naught is equal to 1 over V, and I can set those two equal together. I have 1 over V is equal to mu naught epsilon naught times V, and if I solve for V, the velocity is equal to 1 over square root of mu naught times epsilon naught, and these are just constants, mu naught and epsilon naught, and so the velocity of all electromagnetic waves is 2.998 meters per second squared, and that's approximately equal to 3 times 10 to the 8th meters per second squared. Or I'm sorry, meters per second, not meters per second squared. We're talking about velocity here. Meters per second. And this is given the name celitas, which means speedy. And this is the speed of light. So all electromagnetic waves travel at the speed of light. And this was an important relationship that Maxwell found based on his equations that proved something that Faraday had been saying for decades, that he believed that electromagnetic waves, or light, was just a form of an electric field and a magnetic field, and he believed that they were one and the same. And Maxwell proved him to be true.